This is IAT355 Visual Analytics, Lecture 5.2, and in this lecture segment, we're going to be talking about perceptual properties of lightness and color. So the key perceptual properties that we are all using when we're doing visual analytics, particularly when we're thinking about visual design, are brightness, color, texture, and shape. In this lecture segment, we're going to be concentrating on brightness and color. And part of the reason for that is fundamentally we're interested in the properties of light and the properties of light that we can perceive. So we're going to talk briefly about the properties of light and the names for how we perceive light, as well as various colors. So let's just talk about these two closely related terms, luminance and brightness. So luminance is the measured amount of light coming from some place, say from a light source or reflecting off a page or a wall. And brightness is the perceived amount of light coming from that source. They are not the same thing. And in particular, our perception of brightness is very much dependent on the visual context that we live in. And that's the reason why we wear sunglasses, so that we can adjust our perception of brightness and still see the world reasonably well. So the perceived brightness is a nonlinear function of the amount of light emitted by a source. And it is typically a power function. So the sensation S is equal to some constant A times the intensity to some power. And what that means is it depends significantly on the intensity, but the power here is not a square, but it is a smaller number, less than 1. It indicates as sensation intensity increases, perhaps quite significantly, our sensation does not increase so rapidly. It adjusts to the fact that there's a lot more light coming to the eye. And the reason for this adjustment is because if you don't have an adjustment like that, then we would be only able to see anything within a narrow range of brightnesses. And that's not a way to succeed. So the eye adjusts for a wide range of absolute brightnesses, of absolute luminances, absolute intensities, to give us a sensation that enables us to adjust to what's going on in the visual world. And once again, it's very different on screen versus on paper. So grayscale is probably not the best way to encode data all by itself because of contrast issues. And surface orientation and surroundings matter a great deal, and we're secretly demonstrating that as we go through these slides. The luminance channel of the visual system is so fundamental to so much of perception that we can get by without color discrimination, but not luminance. And luminance and brightness is a very important factor in our way to visually understand the world. So, when we're talking about grayscale, an important thing that point I've been making throughout this early part of the lecture segment is that black and white are not fixed. They're very much dependent on the context, the visual context of the environment. And to illustrate that point, I don't know if you've noticed, but I've subtly changed the background color for each one of these slides, starting from slide number 2. Let me go back and forward. And you might not have noticed that change because I've tried to make the change to be a small amount. What happens is that every time I move the slide forward, I decreased the luminance of the background. And probably you didn't notice that I was changing that. You might have noticed that there was something happening, but you probably weren't able to put your finger on it. And this happened because of all of our natural ability to adjust rapidly to the visual context in which we live. That rapid adjustment to visual context is something that we always have to watch out for as we are interacting and creating visual displays. One of the fundamental elements of luminance is that's just part of the picture. When we're designing anything visually, we also have to make sure that the stuff we're drawing is easily distinguishable from the stuff that provides the background or the framework for perceiving the visual elements. And so Here I'm just illustrating that once again, that the foreground must be distinct from the background. So in this little image, what I'm doing here is I'm drawing the same yellow colored text. Can you read this text? Repeated all the way through here. And probably on this segment, you can read this text because it's a light yellow on a dark green background. But as I lighten up the green, there comes a time in which it's hard to read what this is, even though you know what it's saying. And it's hard to read this one as well, even though the background color is white instead of green. So what this says is that the context of visual display, the background colors, and the visual environment is very important. And in Tableau, you can see that they've taken great care to control the visual background of everything to be very, very muted and very narrow in its use of extreme colors, because extreme colors don't help with visual perception. So, now that we've talked briefly about luminance and brightness, let's talk a little bit about color. So you've probably seen this a few times. This is a model for perceiving color and representing color called the HSV system, which stands for hue, saturation, and value. It is an approximation of the way our eyes work. It is an approximation of the space over which we can perceive color. I say an approximation because a diagram I'm going to show in the next few slides is a more thorough approximation, but its shape is not as convenient as this one, which is a cone which stands on its apex, on its point down below. So there are three elements to this cone. It's a 3D shape, which has been represented on this 2D screen. At the apex of the cone, and running up through the center of the cone to the top flat part of the cone, is the value dimension. And value is equal to brightness. That is to say, the perceived brightness of what's going on in the color. So a single value of V that is at its maximum is getting closer to white. If V is a small value, it's closer to black. Hue is the spectrally pure color that we can see. We think of that as these nameable colors we're all familiar with, particularly from the rainbow. So we have red, orange, yellow, green, blue, indigo, and violet over here. Those are the colors of the rainbow, and they are arranged in a circle around the periphery of the cone. And saturation is the purity of the color. Unsaturated color is very close to white. That is to say, it has lots of other colors mixed in, and as you add more and more colors, add more and more light into the scene, you get closer and closer to white. The more saturated the color is, the more towards the periphery or to the edge of the cone is, and the more close it is to a spectrally pure color, say red in this case, where the S arrow gets to. So the HSV space is a three-dimensional space where the apex of the cone indicates black and the top of the cone indicates the brightest colors and the purest white, as it were. This is derived from the CIE space, of which we're showing in this diagram a duplication, but with more or less smooth colors shown on the left and segments indicating color names that we would assign to those things on the right. And the CIE 1931 RGB color space were created by the International Commission on Illumination in 1931. They resulted from a series of experiments done in the late 1920s by William Wright and John Guild, using a bunch of observers, folks who are looking at color reproduction apparatus and telling the experimenters what colors they could see and what extremes that they were able to perceive. So the CIE space that we're showing here is a perceptual space. The dimensions of this space are a little bit interesting. They are X and Y, and there's a third dimension that's not shown because this is just a 2D rendering of the chromaticity diagram, which is just the colors alone. What's inside this horseshoe shape are the range of colors that are perceivable. In the center, you see white. It's not quite at the geometric center of this diagram, but that's the blend of all the possible colors, that is to say, all the possible colored lights that add up to white. Over on the left, we see, in the bottom left, we see the blue end of the spectrum, and around the smooth periphery here, we see the progression of light wavelengths from 400-ish to 500, down over to here to 600 to 700, and those are the spectrally pure colors, the kinds of colors that you would get by shining a white light through a prism. So this is pure spectral blue at wavelength 480 right here. There's no other color, no other colored light that is present when an observer is looking at light like this. So around here is the spectrally pure colors, and in the middle are blends of various colors, various colored light to be able to be perceived by a viewer. So over here on the bottom left, you can see blue, and it has a fairly large range of wavelength values from the low 400s up to 500, whereas in the greens, we're very sensitive to green and very capable of distinguishing very small changes in wavelength and distinguishing those as different greens. Our sensitivity declines a little bit as we get closer to red, but our sensitivity of red is much greater than it is in blue. The straight line between blue and red here, those are not on the spectrum per se. Those colors that are along this line are a blend of blue and red. Over on the right, we can see this diagram has been segmented with swatches of this being identified with a color that we would commonly name in English. So green is here, and red is over here, purple is there, and so on and so forth. What I'd like to do now is to show a video which explains the chromaticity diagram and the range of perceivable colors. And it is by SMC 468 Graphic Design for Education. I discovered this, and it's a really good video that explains the chromaticity diagram. So here we go. So the chromaticity diagram it is a graph that shows all the possible colors. Each color is defined by a pair of numerical coordinates, x and y. And you can use the chromaticity diagram to see how light blends together. Once again, points on the curved border are pure spectral colors, the colors of the rainbow. A straight line between any 2 points in the diagram shows the colors that can be produced by mixing those 2 colors, that is to say, mixing lights of those 2 colors. So here are 2 pairs of lights, blue and yellow, and I guess purple and something. Different points on the line represent different mixtures of the 2 colors at the endpoints of the line. Note that any color in the diagram can be made in different ways. And here there's a color we're kind of having where all the 3 lines cross. We can get that color by any pair of line segments joining any 2 points on the periphery of the diagram. If we extend this to 3 colors, we get what's called a color gamut, which is a range of colors. And this is one of the principles behind RGB color. Here's blue down here. We'll soon have red here and green there, and red, green, and blue lights mixed together add up to white in the middle, and that's the basis of RGB displays, like the one you're now looking at. So using these 3 colors covers the largest possible area of the chromaticity diagram, but it doesn't cover all of it. And it's technically difficult to produce screens that generate pure spectral colors that are red, green, and blue. So color gamuts of real displays tend to be a little smaller, the way it's shown here. To fully specify your display, you'd need to be able to identify what reds, greens, and blues it can reproduce. And standardizing colors is difficult because each display has a different red, a different green, and a different blue, sometimes from one serial number of a display to another. So one of the drawbacks, I'm sure you're aware of this, but a computer monitor cannot depict all the colors that you can see. In particular, in the curved regions, it will miss. And another aspect of it is that the range of brightness is also hard to reproduce. You can also generate color by mixing paints, and so it's cyan, yellow, and magenta that you would mix together. And as you add paints, that's subtracted color yielding black. Okay, so that's a brief review of the chromaticity diagram from CIE. It's a nice It's a nice video, and if you want to see it again for yourself, there's the URL that you can select, and that'll be uploaded to Canvas as well. So given that the range of colors that we can perceive, that people can perceive, is very large, and RGB and other types of displays have a limited amount of that entire space to be reproducible on the device, an interesting question does come up. What kind of colors can you produce? And in addition, what kind of colors can you end up coming up with reliable names for? Because in visualization, one of the things that we use color for is to distinguish different categories of things, or different names for nominal data. Categories for categorical data, names for nominal data. And so an experiment done in 1986 had people name different colors on a monitor using an RGB monitor. And what they discovered was that there are some colors that people call blue that actually have a fairly large range of RGB values. Clearly, the blue value will be large here, but there's quite a few colors in which there's a lot of green in it, perhaps not so much red, that people perceive as blue. And once again, that's a reiteration of the point that we're aware of, that people have a hard time distinguishing one blue from another. But we're pretty good at distinguishing red, distinguishing green, and also very good at distinguishing yellow, because that's a mix of the, the two kinds of colors that we have an easy time perceiving. White and off-white are also fairly easy to perceive, and so that's why you see a small region here. Okay. So the reason why we care about color for categories is that what we'd like to be able to do is to be able to identify a color, visually associate it with a category that we have in our data, and when we see the color, come up with category. When we see the category, come up with a color. So we need to, move back and forth between the visual representation and the idea of whatever it is that we're visualizing. And so, what number of colors can we use? Well, the Colin Ware came up with a suggestion, and that is to use 12 colors. And this is based on a series of experiments he did in the 1990s. And what he discovered was that there are about 12 colors that you can reliably name and use as category colors. And they are red, green, yellow, blue, black, and white. And so they're the colors you might come up with, the ones you might name if you were asked to name some colors. They're the primary colors, the additive primaries, red, green, and blue, and with the addition of yellow. If you wanted 12 colors, you would add pink, cyan, gray, orange, brown, and purple. And those colors work with a white background, shown here, and also work reasonably well with a dark background. So he did an experiment where the background color was used as a backdrop for color pairs, and he wanted to find out which colors would be easy to distinguish from each other. Why 12 colors? Well, the answer is that our perceptual system, because of its relative nature, adjusts itself continuously to the visual environment. So here's a question. Of these two gray squares, which one is brighter? Now, you've probably come up with a conclusion. It turns out the one on the right is brighter. The RGB values on the left are 130, 130, 130. On the right, it's 140, 140, 140. And the reason those might be hard to distinguish on your monitor, well, my monitor I can distinguish them just about, is that there is this discovery that has been known for a long time called Weber's Law. In the 1830s, Weber made measurements of what is called just noticeable differences in perception. He was asking people to notice differences in weight, differences in length, and in other things that you can perceive, color being one of them. And he found that for a range of stimuli, the ratio of J and D, just noticeable difference, delta S to the initial stimulus S was relatively constant. That is to say, delta S over S equals K. Each constant depends on the thing you're trying to judge. So weight's value of K is different from the judgment of the K for length, which is different from the K for color. So what that means is that ratios are more important than magnitude in stimulus detection. So, for example, We detect the presence of a change from 100 centimeters to 101 centimeters with the same probability that we detect the presence of a change from 1 to 1.01 centimeters, even though the discrepancy is 1 centimeter in the 100 centimeter case and 0.01 centimeter in the second case. It turns out that our ability to visually detect length is actually really good. So this is a very good ratio, 1% or 0.01. But for others, what happens is that our delta is somewhat larger. The other thing that's kind of an outcome of Weber's law is that most continuous variations in magnitude are perceived as discrete steps. And this has salience in all sorts of things, visually and in other areas. So for example, contour maps, font sizes, and here, this color ramp. Depending on the size at which you're watching this, you might see 5 or 6 or maybe 7 independent blobs of color, even though this color thing here, this monochrome color ramp, is continuous in terms of pixel values from 000 to 111. And what happens is that this ends up looking quantized, like this. The quantization is something that your perceptual system is doing. It's not something that is built into the monitor. It's about what you can perceive. And it's interesting that when you look at this, you kind of sometimes can oscillate between seeing this thing as continuous and seeing that maybe there's bands of color. The bands are illusory. They're a result of your perceptual system doing its work. So that's it for lecture 5.2, where we talk about perceptual properties of lightness and color. Our next segment, we'll talk about nonlinear perception. We were just sort of leading up to that conversation in this section, and we'll pick it up again for lecture segment 5.3.